it'll be there. Okay. They finally done what they've been hinting they were going to do. They have removed all the unpaid students from the rolls. Now, I don't think that pertains to any of you, but you will know that. I won't. When I look at the rolls next time, I'll know whether you're on there or not. So hopefully you are still on there. If you're not, get your payment completed, and I think there's a way to get back on the roll, but get it done, and then fiddle with them, talk with them, fuss with them, beg them, whatever it takes, but try to go from there. Okay. Last time we left off, any questions on anything we've done so far? Okay. There was a question in the last class, and I hope it's fairly clear. It's sort of a good news, bad news situation coming up next week. The bad news is that Thursday of next week is the 4th of July, and there's no school. Okay, the college is closed on the 4th. The good news is it doesn't affect us any. We have class Monday and Wednesday of next week, so you don't lose a day. I knew you were worried about that. So that's taken care of. Now, can't think of anything else along those lines. Here is Marjorie. Okay. Now, I had a question pertaining to the second test. I had forgotten that a question similar to one that we did last time was on the second test, and I got sort of frustrated with the book in that they left out so many steps, not realizing that was probably going to be frustrating to you too, because your test question, they left out so many, well, of course the steps aren't given for it, but there's nothing to follow in the book on it. So let me, all right, let's do on page 546, I know we already did part of this problem, but I'll try to do it a bit more completely, because I was, it's sort of a pain in the neck problem, okay? But since it's on the test, we need to do that. So let's, what we have here is a sealed barrel of oil. This is on page, oh, I started to write this. This is page 546. I can't write. 46. This is example 6. Okay, it's not one of the homework problems. It's this, and this is whole, right? It's. Make sure I'm marking the right person. Okay. All right. I think I've got everybody. No one new comments, just a call roll. Okay. Now. Okay. My picture's going to stink, okay? I guarantee you that. Here you have a barrel of oil floating in water, okay? And at the very top of the barrel, there's a little air space. Oil is inside, water is here. So this is water, this is oil in the tank, okay? Now, the oil has a density of 48 pounds per cubic feet. So and let's see, this is where I tend to use my units, and I want to make sure we don't deviate too far from, do they even use a symbol for density? That's what I was trying to remember. I'm just going to use mine. The density of oil is, they tell you this right at the top, 48 pounds per cubic feet. 48 pounds per cubic foot. Okay? Floating in seawater, now this is seawater, and the density of seawater is 64 pounds per cubic foot. Okay. The barrel is not completely full of oil. Okay. The barrel lying on its side, with the barrel lying on its side, the top 1/10 of a foot of the barrel is empty. So I'm going to do the same thing they did, show you the end view here. And the end view, if that is the barrel, and they're going to put the coordinate system smack through the middle, which I didn't quite hit, but let's just pretend I did. Assume the radius of the barrel is 1 foot. So I think we did this assumption before. R is equal to 1 foot. Okay. Now what they said, the top 2/10 of a foot of the barrel is empty. Okay. So here, this is 0.2 feet. Okay. Not got oil in it. Okay. Compare the fluid forces against one end of the barrel from inside and outside. Assume the radius of the barrel is 1 foot, and with the barrel lying on its side, the top 6/10 of the barrel is above water. So the water line is about here. So from here to here is 0.6 feet. The top 6/10 of a foot of the barrel is above water. Okay, so this is the oil, this is seawater. Okay, ugly picture, but hopefully you can follow what's going on. Okay. And they suggest you put the coordinate system through the center of the barrel, which is a good idea. Okay. Now, with that in place, like that, then these coordinates here for the barrel, that fits the general equation x squared plus y squared is equal to 1, because that's the radius of the barrel, 1 squared foot. Okay? Now, it says to find the fluid force against one end of the barrel from the inside. So in this case, we're not looking at the water at all, only the oil. Okay? To find the fluid force against the end of the barrel from the inside, integrate between, and of course, if your origin's there, you're going from -1 down here to positive 0.8. So that's your range for oil. That's what's giving you the pressure from the inside of the barrel. Okay? Now, for any given, and by the way, you're going to do dy's, and there's obviously a reason for it to be dy, because in this narrow strip, the pressure is equal. If that's narrow enough, the pressure is always the same at that level. You can't do horizontal strips because the pressure would be greater down here than it would up here. So you can't do that. You have to do horizontal strips. Now, I did a lot of this last time. I can't remember how much I did and how much I didn't. But if you go back to the, I'll just point you this direction. They point you back to section 7.7 where we did the general equation. I didn't want to redo all that, but the general equation for finding the force, okay? And here was that general equation. The force is equal to, here, I knew it was wrong. The book uses W, I knew it was in here somewhere, for the density. And I don't know why. No physics book I know of uses that. But this is, yeah, W. which is the weight density. That's why they use W, weight density, as opposed to mass density, okay? The weight density of the oil. So this is equal to W, and this will be W for the oil because we're doing the pressure from the inside. See, that's constant. It's constant. Now, we're not making any assumption that it's a little denser at the bottom than it is at the top because it's got more weight. No, we're going to say the density is the same throughout. And that's a very safe assumption, okay? So, since that's a constant, it can come to the outside. Okay. Again, though, the density is pounds per cubic feet. Your force, that's in pounds. So everything inside here had better have units of cubic lengths. In other words, cubic feet. Because this is pounds per cubic feet, this will then give you this in pounds. Now, I'll guarantee you one of them is going to be your dy. That's going to be a length measurement. So that's the last one, dy. Okay? Now, we've got to figure out the other two. Okay? Well, one of those is the length of this strip. Okay? And the other is going to be the depth of the strip. Okay? And you need both of these to be functions of y. And I think we went through this before. From this triangle right here, you know this side is always 1. This is your y value, whatever that is. And then this is, because of your the fact that it's a surface on the border of a circle, this is going to be, this value here, this x here, is going to be the square root of 1 minus y squared, right? Pythagorean theorem. This squared plus that squared is equal to 1 squared. So this is y, so this one is the square root of 1 minus y squared. So that's the length there. Now, you got two of those, so I would take the 2 on the outside with the w, okay? Oh, and what are your limits of integration? As we just said, minus 1 on the inside to 0.8 feet. Okay, these are in feet. All right, now, I guess I just put my pen down here, but that is a weird looking little mark there. I'm going to take it out. Okay. So this length is twice this, so you got the square root of 1 minus y squared. That's one length measurement. The book calls it L of y. And the other is your depth measurement. Okay? How deep in the oil are you? Okay? So that's the 0.8 minus y. That's how deep you are in the oil. And now this y I wrote here happens to be negative, so 0.8 minus or minus y, 0.8 would be that far, minus would be that far. So it's the upper minus the lower. So that gives it to you, whether you're here, or here, or here, or here, wherever. 0.8 minus y is the depth of the oil. And the book calls that, I think, H of y is what the book calls it. So that's a 0.8 minus y. Okay? Now, is that the part that was giving you problem, or what goes on from there? Huh? I can't hear.
Like setting it up like this.
Setting it up. So is this enough? Can you do the, or you want to see some more of it?
Yes.
Huh?
That's enough.
That's enough? Okay. And I think the one on the test didn't have inside and outside. It was just, what's the pressure on it? Wasn't it? I think so. From the outside, the difference would be that you use the the density of seawater, that would go out there, and your limits would go from 0 to 0.4. I mean -1 to 0.4, because that's the only part that's under seawater, but the rest of it would be pretty much the same. Okay. All right. Is that enough? Okay. Any other questions on this? And they left off steps after step after step, but hopefully you can follow it okay. If not, I'll try to do some of the other parts of it. If it's the integration that giving you fits, we could try to do that as well. No more? Okay. If not, okay, where we left off last time, we had done example 3 and finished it on page 555, top of 555, and we're getting ready to do example 4. And if my memory's right, example 4 is not on here, right? So let's go back, just like we were doing before, and do our example 4 there. All right. Jump from fluid forces back to partial fractions. Okay? Here's example 4. Find the integral, excuse me, 8x cubed plus 13x divided by x squared plus 2 squared dx. Now, what's a good question to ask yourself first?
Can you factor out anything?
Second, okay? Can you factor out anything? That is usually a pretty good question. The answer is you can factor out an x in the numerator, leaving you 8x squared plus 13, which is not going, neither one of those are going to show up in the denominator, so it doesn't really do you any good, but it's always a good question to ask, okay? Next. Okay, the degree of the numerator, it better be less than, not less than or equal to, less than the degree of the denominator, is it? Yes, because this is x to the 4th. If you multiply that out, don't multiply it out, but if you did, that gives you x to the 4th. Up here you only have x cubed, so you're okay there too. And Ricky's here. So we're really okay. Now, what next then? You've determined, you are set up that you can use partial fractions. How do you use partial fractions? Say again? Okay, yeah, and that's a good point right there. So here's what we do. Now let's just take the whole fraction here. We'll put it back in the integral in a minute. Let's just take that fraction. 8x cubed plus 13x over x squared plus 2 squared. Okay? I can tell you right now, I'm not going to like this one very much. Okay? I can see already it's not going to be a fun one. But we need to know how we can break that down. Now, number one, ignoring the square here, that is an irreducible quadratic. You can't factor that any further. Even with square roots and stuff, you can't do it, okay? Because that has no factors, okay? If you did the, nowhere you can go with it, okay? So what would be the procedure for breaking this down into a partial fraction decomposition, it's called? I heard the A. That's all I heard though.
A over.
Okay, no. Okay, this is a quadratic. So your numerator has to be 1 degree less. So it has to be linear. ax plus b over, now continue, x squared plus 2, good first step, plus cx plus d over x squared plus 2 squared. Okay? Anytime you have a repeated factor in the denominator, you do first the first factor with whatever is required. If that had been a linear thing here, just an a would work. With a quadratic, ax plus b has to be there. But then for every one of these, you have another term that's just like it, except you go up to the denominator by 1 power at a time until you reach the max. Fortunately, this just had 2. Okay, so that's it. Okay, what's your next step? Multiply, get rid of those denominators, okay? So multiply the numerator by x squared plus 2 squared. Multiply the first term by x squared plus 2 squared. And the second term by x squared plus 2 squared. All right? This whole denominator goes, okay, leaving you just 8x cubed plus 13x equal. Now this one, only one of these factors goes, which leaves you a foiling problem, and that's not too bad. Let's go on and foil it. That's ax cubed, agreed? Okay. Now I'm going to do the squared term next, because this isn't going to spell foil rightly, but we'll do it. Plus bx squared. Then my x term next will be plus 2ax. With me so far? And then the constant term last, and that's going to be, I got them, don't have my smiley face now anymore, plus 2b. With us there? All right. I'm not going to have room to do everything. Oh, the good news is the whole denominator goes here, so all you have left is plus cx plus d. Yes, I do have room. All right. Remember back in the good old days when we had one of our factors that we said, well, let's pick a value for this and set it equal to, make it equal 0. Don't have any of those. There's nothing you can say let x is equal to that's going to make that thing equal 0. Not going to happen. Okay? So what you have, what you're going to wind up with is a 4 equations, 4 unknowns. A big boo hiss, right? What's the first one of those? It's not too bad. There's only one cubic term. So what does that tell you? They have to be equal. They're on either side of the equal sign. A is equal to 8. Okay? That wasn't bad, was it? Okay? Now, oh, the next one's not too bad either, is it? B is equal to 0 because there is no square term on this side. So that's not too bad. Okay, we get into a little bit of problems with the linear terms. What is it on this side? 2a plus c has to equal 13. Do you agree? But we already know what a is, don't we? This would be 2 times 8 plus c is equal to 13. Think y'all can work that out, can't you? What's c equal to? Second? -3. Good deal. This isn't going to be nearly as bad as I thought. C is equal to -3. Okay, and then the last one. Some more good news. D is equal to 0 because there is no constant term on the left-hand side. So this isn't too bad. So far, our integral is now, A would be 8x over x squared plus 2 dx. I don't need the parentheses down there, but I'll put them in there anyway. And then your next part is plus the integral. And your let's make it minus the integral. And I'm even going to go and take out the 3 because I know I don't need it in there anyway. I wish I'd have done it with the 8. And that would be dx over x squared plus 2 squared. Did I do that right? All right. Now I'm a little glad I didn't take the 8 out because I don't want all of the 8 out there. All I want out there is a 4. And that's going to leave me with a 2x over x squared plus 2 dx. Now over here, we got problems, don't we? But I think we can deal with them. We'll just leave that empty for a bit. What about that first one? First integral. Yes, let's try a u substitution. Let u equal what? X squared plus 2. Then du is equal to 2x dx. You see why I was psychic and saw that I only needed a 2 up there? Yes, 2x, because we got 2x dx. So this one right here is going to be 4 times the integral of 2x dx is your du, and your x squared plus 2 is u. And what's that going to be? Log u. We'll put absolute value for now. But what is u? 4 times the log of x squared plus 2, which I took off the absolute values. Why? Always positive. X squared can't be negative. Add 2 to it. It can't even be 0. Okay? So, we're perfectly. So this first one we got. Now, we got to mess with that next one. And that's going to take some messing. So let me erase some space here. Is it all right to get rid of these? We already put them in place. So we'll get rid of those. Somewhere we'll get rid of them. And we're going to get rid of those because we've already put those in place. Okay. Now, what in the world does that look like? Let's just go over here and just deal with this. Let's just deal with the integral. We'll come back and put the 3 in there later. The integral of dx over x squared plus 2 squared. Anything come to mind? If a u substitution comes to mind, let it lay down until the feeling passes, because it's not going to do you any good. Okay? What might work? Second? Yeah, you got it. Trig substitution. Let x equal, now this is where it gets a little bizarre, the square root of 2 times the tangent of theta. I think you'll see where that comes into play in a minute. What's your next step? Dx is equal to square root of 2 is still square root of 2. Second, secant squared theta, d theta. Okay, we've taken that to its extreme. Now, sort of on the parallel side, we want to square this. So x squared is equal to what? If that's x, what's x squared? 2 times what? Tangent squared theta, right? But we also want to add a 2 to that, which gives us a plus 2 here too, right? All right. Let's just deal with that for now. And probably at some point we're going to need our little triangle. So let's go on and draw our little triangle. Okay, this is our theta, and our assumption here is, get out of there, is x is equal to the square root of 2 times the tangent of theta. That means, where do I write it? The tangent of theta is equal to x over root 2. Don't worry about root 2 being in the denominator. That tells us that tangent is the what? In terms of opposites, adjacents, and hypotenuses. Opposite over adjacent. So this would be our x, this will be our square root of 2, and this is the square root of x squared plus 2. Isn't that nice? That's exactly our denominator. Okay, so we'll come back to that if we need it. All right. Now, let's continue with this. We wanted to take a square root of that and a square root of this. Okay. Now, we can factor out a root 2 and leave us with tangent squared theta plus 1. And what is that, by the way?
Secant squared.
That's your secant squared theta. And you take a square root of that, and you get root 2 times secant squared theta. All right. Now, I think we're ready to plug in our integral. The dx is, I'm going to pull out the root 2. I wish I'd have left more room. Secant squared theta d theta. Okay, that's your dx over x squared plus 2. Wait a minute, folks. You let me get away with that? We're not taking a square root of anything here. What were you thinking? Okay? It's just x squared plus 2. Okay? We're going to square it in a minute. And this would be 2 times that, which is 2 times secant squared theta. But then we're going to square this. So this will be 4 secant fourth theta. Right? Okay. So that's what goes in our denominator. I'll bring the 4 on the outside, and what's left on the inside is secant fourth theta. Now, did everybody follow my error and everything there? Your x was square root of 2 times tangent of theta. We squared it and got 2 times tangent squared theta. Added 2 to it, and then ultimately we're going to square that. But before we do that, factor out the 2. That's 2 times tangent squared theta plus 1. That's 2 times secant squared theta. I'm going to get a wavy little line in there. I don't know what that was left over from. I think I do, but just get it out of there. Okay. So that's 2 times secant squared theta. But that was that not squared. When you square it, you get 4 times secant fourth theta. That was exactly your denominator. So we plugged in the numerator, which is just the dx, root 2 secant squared theta d theta, and your denominator was 4. Bring that on the outside of the denominator, secant fourth theta. Now, what happens there besides magic? This secant squared goes away, and you're left with a secant squared here. And frankly, just between you and me, I don't like integrating secants much at all, especially when they're in denominators. So what's another way of writing, let me write down this, square root of 2 over 4. Another way of writing 1 over secant squared theta. Yes, that's cosine squared theta. Okay. Now, if we had more room and the inclination to do it, which I have neither, there is a fairly simple way to do cosine squared theta. We've done it. Remember, it's that half angle formula type thing, and it's quite doable. Even easier than that is looking at it in a table. Okay? And boo-hiss is not in the one in the front of the book. That just gives a few of them. So go to the back of the book. If you got a book, all books have them somewhere in them. All calculus books have these tables in them. It's just finding them, I think. Where is it? There it is. Okay. Sine or cosine. Cosine squared theta du. In our book, it's on page A5, which isn't very helpful, is in Appendix B. Forms involving sine u and cosine u. The integral of cosine squared u du is 1/2. So this one here, I'm going to bring it up here and do it. That would be, okay, we have a root 2 over 4. Okay. And you're going to have a 1/2, so that's going to make it a root 2 over 8. Okay. All right. Then what you have after that is u, well, we're calling it theta, so we'll just call it theta, plus sine theta cosine theta. And then they put their plus c. And we've got to do that at some point, so I guess we'll put it now too. Okay. Not going to worry about that right now. Okay. Now, first thing we got to do, figure out what theta is. Go back to this definition term here. Actually, this one right here. That's even better. Theta is equal to the inverse tangent of x over root 2. Okay? Got it? Now, the second part, sine theta. How can we figure out what sine theta is? Our handy-dandy little triangle here, what would that be? It's plus, well, I should do it separately, but I think I'll do it together. Plus, and what sign? Opposite, which is x over hypotenuse, which is the square root of x squared plus 2. That's where the square root comes into play, okay? But it won't be there for long, because the next one is going to be cosine theta. And what's cosine theta? Which is root 2 over the square root of x squared plus 2. Okay? Sorry that it's up there in all the mess. Okay? And then we'll do the plus c later. So this is it. Let's clean that up ever so slightly. And that will be inverse tangent of theta of x over root 2. I'm not too worried about radicals in the denominator, except my radical didn't show up. Okay. Plus, now these two are going to multiply together. Goodness gracious. All right. And that's going to be, I like to write it x root 2. Just because writing root 2 in front, it looks like the x is under the radical. It's not. And when you multiply the denominators together, you just get x squared plus 2. Okay. Now, that we're going to now multiply by root 2 over 8, but also multiply it by minus 3 down here. So if it's okay, I'm going to erase a little bit of stuff. Is that all right? The stuff where we did the trig substitution. Because it's going to run together like crazy. And that's one huge disadvantage of writing all over the board. It's so easy to lose coefficient signs and things like that. But I just don't have the room for it. So that minus 3 that we had from here, and then the integral that had this in front, which I just erased most of it, but there part of it is. So you combine those two together, and it's 3 root 2 over 8. Okay? Times theta. Oh, no, we already know what that is. It's inverse. I was looking at the wrong place. Inverse tangent of x over root 2. I'm sort of tired of writing that. You could write root 2 over 2 or whatever. Okay? Plus, and these we just combined together and did x root 2. There it is up there. Over x squared plus 2. And then finally, we have our plus c. Now I sure hope that's the answer. If it's not, I'm not wanting to go back and find where I made my mistake. Okay? Oh. Yuck. Okay. I wrote that on the wrong place. Well, it's an okay place. Let's get it all together. And I'm going to erase most of this stuff. Is that all right? Because we've already long past used that. Okay. So, our final answer is now, do they leave the 4 in front, or do they put it as a coefficient? No, they leave it in front. 4 times the log of x squared plus 2 minus 3 root 2 over 8 times the inverse tangent, or arctangent the book likes to use, of x over root 2 plus x root 2, the book probably writes it root 2x, over x squared plus 2, and then plus c. Let's see how close we got. Oh man. Yuck. 4 logs x squared plus 2. That came out okay. I wound up with a root 2 that is unaccounted for. The 3 and a 2 in the denominator. I kind of messed something up there, I guess. Wait a minute. I really botched up here somewhere, but they skip so many steps I can't find where they are. Let's see, we had a is equal to 8, b is equal to 0, c is equal to negative 3, d is equal to 0. Yeah, we had all that. Oh man, I don't believe I did that. I've already erased it, but this had an x in it. Why didn't someone catch me? Goodness gracious. Because it was a 3x. I've already erased that part, but remember this was 8x, the a was the, and this was a minus 3x. I left off the x here. And that would have been a u substitution so easy. You made me do all that work just because you wanted to see how to do one like that, and it was totally unnecessary, okay? Because that's another really simple u substitution. Let's do the right problem this time, not the wrong problem. Yeah. Okay. I'm going to disavow any knowledge of this if you're caught or captured that I ever did anything so stupid. But you did see how you could do it if that had been the case, which it wasn't the case. So let's get that out of there. All this is unnecessary. And that's unnecessary. This was unnecessary. Y'all just let me go on and on and on and on and on. This was out. It's amazing how similar some of it came out, though, but that was good. We had that. This is the part that's not necessary. I should have left it 3, but I didn't. Okay, the rest of that is good. Okay, yuck. Same thing here as before. Same u substitution and everything. Okay. This one right down here. I don't want to reinvent the wheel. Okay. So it's a minus 3. And what we're going to have here is the integral of, this is our du, right? 2x dx. Oh, wait a minute. No, wait. That's where my over 2 came in. Messed that up. Right here, here's where it varies slightly. Here you only have x dx, here we have 2x dx, so here we divide by 2 for this part. I can't get the 2 to show up down there. Okay, so this then puts over 2, and that's where the 2 showed up in the denominator before. Okay, now this will then be, just this part here, it's minus 3 halves the integral of du, because you already pulled the 1/2 out, and this is u squared. Right? Okay. Now, I think even I can do that one maybe. Minus 3 halves. What's the antiderivative? Goodness gracious. I erased too much and not enough at the same time. Okay. You could rewrite this as integral of u to the minus 2 du. And what would that be? Second? Okay. A little bit louder. Okay. Yeah. Minus, okay, we're just doing that part. Minus will make that a plus, and that would be u to the minus 1. Plus c. Okay? So this will be plus 3 halves. And what is your u? X squared plus 2. So it's 1 over x squared plus 2, then plus c. So for that part, let's just write it down, plus 3 halves 1 over x squared plus 2 plus c. Now, oh, written in the wrong place again, okay? So this will be plus 3 over 2 1 over x squared plus 2 plus c. Okay. Now does that come out? 4 log x squared plus 2 plus 3 over 2 x squared plus 2 plus c. Yeah. Duh. All right. Sorry about that. Make sense? Much easier problem this way than the way I did it. Wrongly. Okay. Now, okay, that was example 3. They do have at the top, I mean, that was example 4. Okay, before they get to that guidelines thing, they do mention this again, which we mentioned at the very beginning, and it's this. When integrating rational expressions, which is what these partial fractions do, keep in mind that for improper rational expressions, and they give you an example here, so I think I'll back up and do that. Yeah, that's not what I wanted. Okay, let's clear this screen that we've been using to death, okay, and do this example, just in case any of you had forgotten this. What if your numerator polynomial divided by your denominator polynomial was something like 2x cubed plus x squared plus minus 7x plus 7 divided by x squared plus x minus 2. Now, if you had something like that, what's wrong with the picture? The degree of the numerator is greater than the degree of the denominator. Now, there's a couple things to consider if you can do them, and you're not always going to be able to do them. That denominator, I believe, is factorable, okay? Plus 2 minus 1, I think that'll work. But I can't look at that numerator and tell if it's factorable or not. I don't think so. Okay? So I wouldn't waste a lot of effort. If you can see they're both factorable and have common factors, then by all means eliminate common factors. This I don't think does. That numerator is not even factorable as far as I can do it right now, so I'm not going to mess with that. So what would be the next step here? One of your favorites of all time, I'm sure. Especially since you have calculators that have never done it since the 3rd grade. Long division. Only of polynomials. That was fun, wasn't it? Remember how to do it? Okay. I'm going to do it the old way that I remember. Bring down the house and put the top into the house. 2x cubed plus x squared minus 7x plus 7. Okay? Now that makes a division problem. Okay? Don't let that get in your way. Now, 2 things to watch out for here. 2 really big things. Be sure you don't skip any terms here or here. In other words, if this had been an x to the 4th, you'd have to insert a 0x cubed in there. Otherwise, you're going to get all screwed up. Okay, you didn't have to do that in the 3rd grade with long division of numbers because you had all the digits there. With polynomials, you have to make sure you account for every term in descending order. And that's the other issue, that you have them in descending order. You don't have these 2 crossed or those 2 crossed. You can't do it. Be sure they're both in descending orders of the power and you're not missing a power. If you are missing a power, insert a 0 with that power in it. Okay. Now, how do we do division? Adding, subtracting, and multiplying, we usually go right to left, right? Not division. We go left to right. So take the leftmost number, x squared, divide it into 2x cubed. How many times will that go? 2x times. And then what you do after you divide? Multiply. You remember your long division, don't you? 2x times x squared is 2x cubed. It better be. That's why we did it. But then we do the rest of them. 2x times x is 2x squared. Keep them in line. Then 2x times minus 2 minus 4x. Okay? Now what you used to do in long division was subtract because all the numbers were positive and that was easy. Now we have sign numbers, so I like to change signs and add. But if you like subtracting, that's fine with me too. But I'm going to change signs and add. So I'll make this a minus, that a plus, and that middle one a minus. Okay, and it's easy to do when you have erasers like that. Okay, now add. These two go away. They better. That's why you set it up. What does the next one do? Next. X minus 2x. I mean, x squared minus 2x squared. Minus x squared. Next. Minus 3x. Next. Plus 7. Bring down the plus 7. Now, divide again. You keep dividing as long as the degree of your remainder is greater than or equal to the degree of the divisor. It is, so keep dividing. What's next? Minus 1. Then you multiply. Minus 1 times x squared is minus x squared. Next. Minus x. Next. Plus 2. Now change signs and add. I like to do it. If you like subtracting, that's fine. Same thing. Okay. And then you get, these two go away. Good. What does this give you? Minus 2x, and that gives you plus 5. All right. You're done with your division. So what this gives you, and how did you do if you had a remainder? How did you write it? Way back in the 3rd grade? Didn't you write it as plus your remainder minus 2x plus 5 over your divisor? X squared plus x minus 2. Yay or nay? Yeah. Okay. Now, that was the thing we were going to be integrating, remember? So when you integrate this, you just integrate 2x minus 1 dx. And then I would be tempted to pull out the minus here and do a 2x minus 5. I hope that's not too bad. Over x squared plus x minus 2 dx. You see what we did? If this was the thing you were integrating, this thing right here, do your division and then just integrate the quotient. This is simple. That's just polynomial. This then you have to use partial fractions, okay? And fortunately that this factor as x plus 2 times x minus 1, and then you can go on with how we were doing it. Okay? Make sense? You want to see that taken further? They don't do it in the book, so I can't show you what's right or wrong, but you know that's how you proceed. If your numerator, if it's an improper rational expression, okay, meaning the degree of the numerator is greater than or equal to the degree of the denominator. Integrate this x squared minus x, and then whatever that becomes. All right. Now, let's proceed. If there are no questions on that, 2. The guidelines. Here are some guidelines for solving basic equation that is obtained by a partial fraction decomposition. Okay, when you have linear factors in that denominator, substitute the roots of the distinct linear factors into the basic equation. Oh yeah, okay. If it was x minus 3, put in x equals 3. That's what they mean by that. What in the world are they talking about? Into the basic equation, and that makes the calculations for your variable, your unknown, what do they call that? Coefficients, easy to calculate. Number 2, for repeated linear factors, like to the third, fourth, second, third, or fourth power, something like that, use the coefficients determined in the first guidelines to rewrite the basic equation. Then substitute other convenient values of x and solve for remaining coefficients. Now that's one way to do it, or you can just solve system of equations. That both require solving system of equations. Now if you have quadratic factors, expand the basic equation as best you can, collect the terms according to the powers of x, and that's what we were doing. Here's the x cubed term, here's the x cubed term. Set those coefficients equal. Equate the coefficients of like powers to obtain a system of linear equations involving a, b, c, and so on. Then solve the system. Okay? That's real easy to say, and sometimes solving those systems can be a real pain in the neck or other anatomical feature. Okay. Now, there is a little blurb on the margin note here about another method of evaluating integrals of rational functions, alternate approach to partial fractions. If you want to follow up on that and are really fired up about it, you can certainly go for it. Okay? And they give the reference and everything. That's the last thing they show. So let's go back to our favorite slide here. I'm going to hit a little bit more that they don't show on the slide set. Before concluding this section, here are a few things you should remember. First, it is not necessary to use partial fraction technique on all rational functions. Okay? For instance, if you had this one, the integral of x squared plus 1 over x cubed plus 3x minus 4 dx. Okay. Now, to begin with, can you factor that denominator? Really? I'm not sure I can. No, yeah, if that was a squared, even I might be able to do it. But I'm afraid with a cube there, that might be a bit daunting. Okay? So certainly I'm going to look for something easier. Okay? Now, here's what you might choose to do. Let's look at that denominator. That's the problem child here, right? The denominator, because usually we deal with the numerators. So let's look at that. What's the derivative of that denominator? Good old, almost like a u substitution. In fact, yes, you could do it. Let's try that. Let u equal that denominator. X cubed plus 3x minus 4. What's your next step? du is equal to 3x squared plus 3x, nothing else. And guess what you might be able to do with that? Whoa. That's plus 3, yes. I was going to say that better not be an x there, and there wasn't, okay. What could you do with that? Pull out a common factor of 3, and what does that leave you with? X squared plus 1. I forgot my dx here. That's what I meant to write, was a dx. Okay, dx. Okay, and guess what? X squared plus 1 dx, there. All you have to do is divide both sides here by 3, and this would be 1/3 the integral of du over u. And I think even I can do that one. Okay? That's just going to be a simple log of that denominator. Thank goodness. Otherwise, impossible to factor that. Partial fractions was going to be out of the question anyway. Okay? So this gives us 1/3 the natural log of that denominator. The denominator, x cubed plus 3x minus 4. Okay. Plus the, okay. Now, there's one place, especially when you can't factor the denominator, but sometimes even if you can, this may be a good thing. If the numerator looks like it's anywhere close to the derivative of the denominator, then go to your u substitution. That's a easy way to go. All right, let's look at another exception, you might say. It almost feels like English class, isn't it? You get a bunch of exceptions here. What if you had this? The integral of x squared minus x minus 2 over x cubed minus 2x minus 4 dx. Okay. What's the first thing that pops into your head is probably a problem. Just looking at it, I'm really doubtful I can factor that. So I'm going to start looking for other things. But on the good news side, I can factor the numerator. So let's go on and do it. I can't think of anything else to do, so let's do what I can. So what would that be? X minus 2 times x plus 1. Right? Now, that might give me a little bit of hope. Let's just hope, beyond hope, that one of those is a factor of the denominator. I'm going to go to something else in your past. Do you remember synthetic division? No? So you don't remember it fondly even at that. Synthetic division is a really good thing. And I'll give you a real quickie on this one. If you're dividing this into that, you could use long division if you wanted to, but synthetic division is much easier. What you do is take the opposite of that second. Oh, the only time synthetic division works if your coefficient is 1 and your exponent is 1. And both of these factors have that. So that's good news. So take the opposite of your number, minus 1, and go into the coefficients of what you're dividing into, or you're trying to. Well, the coefficient of x cubed is 1. What goes next? You have to account for every term. 0. Then, -2, -4. Okay. Here's a good little thing to do. Count the number of terms here. 1, 2, 3, 4. Ought to be one more than your degree here. Always. Okay, and it is, so you're fine. Okay? Now, my little rule here is skip a line, draw a line. I've never seen that in a book before, and for good reason. It's dumb, right? Then bring down the 1. Now, from this point on, you multiply and add, multiply and add. You might say, wait, in division you multiply and subtract, don't you? But that's why we changed the sign of this one, so we could add. So let's do it. Multiply, -1 times 1, -1, that's why you skip a line. Add, -1, multiply, add, multiply. Bad news, it won't go in. You'd have to have a 0 as a remainder there. It doesn't. So that didn't work. But before we give up all hope, let's just change that and this, but leave that alone, to the other one. And what would that be? A 2. So put a 2 out here. Now let's proceed. 2, 2, 4, 2, 4. Ding, ding, ding. We have a winner. Okay? And what this represents is x squared plus 2x plus 2. You go on and put your variables back in. 1 degree less. Okay? So, at this point, you take a look at that and say, well, can I factor any further? And I believe the answer is no. Okay? So therefore, this is an irreducible quadratic. So we know what to do there. But what we do up here, we rewrite this as x minus 2 times x plus 1. And this denominator now we know is x minus 2 times x squared plus 2x plus 2. Now I wouldn't have really done this, dx, because I knew these were going to factor out. So now our problem is the integral of x plus 1 over x squared plus 2x plus 2 dx. So I take that over here to the side and do my magic on it with partial decomposition. Partial fraction decomposition. X plus 1 over x squared plus 2x plus 2. Someone tell me if that really will factor. I don't think it will. And that's going to be, because that's irreducible, ax plus b. Wait, it really doesn't work if you don't have a factor there, do you? Oh, well then why do that? You don't need this. It won't factor. Don't do that. Have you ever been to the doctor and you said, it hurts when I do this, and he says, well, don't do that? You want to slap those doctors, but anyway, never mind. Not that it's happened to me or anything. But what would you do with this one?
Substitution.
What's that?
Substitution.
Okay, what would you substitute? U equal x squared plus 2x plus 2. Then, what's your next step? du is equal to 2x plus 2. And that's exactly, dx, and that's exactly 2 times x plus 1 dx. And that's what's in the numerator here, so divide by 2. And you have 1/2 the integral of du over u, which is log of u, which is then 1/2 the log of x squared plus 2x plus 2 plus c. The log, 1/2 the log of x squared plus 2x plus 2 plus c. Very good. All right, any questions on that? Erase? All right. One more at the bottom here. Sometimes partial fractions can be used with quotients that are not polynomials. This is a little bizarre, but it is true. The integral of cosine x over sine x times sine x minus 1, okay, all that's times dx, okay? Now, If that was your problem to begin with, what might be your first step? I was expecting Marjorie to pop up. Yeah, why not try a U substitution? What might you try? Let U equal sine x. Then du is equal to cosine x dx. Okay? Well, guess what we've got then? We've got the integral of du over u times u minus 1. And that's just set up perfectly for partial fractions. Right? And that would be pretty easy to do. They don't take it any further, but it would be pretty easy to go from there. Okay? Now, always step back and look at the whole forest and don't get too confused by the trees. Trees can confuse you. Get the big picture. And say, well, wait a minute. You can do this. All right, that finishes 8.5. Homework exercises here include any of the odds 3 through 19. They're all at Calc Chat. 7's at Calc View. Either 21 or 23, they're both at Calc Chat. 21's at Calc View. Any of the odds 25 to 31, they're all at Calc Chat. 33 or 35, they're both at Calc Chat. You can explore doing either 37 or 39. They should be at Calc Chat. Do either 41 or 43. They should both be at Calc Chat. Try any of the odds 45 through 51. They should all be at Calc Chat. Okay. Now let's see what else they've got here. I think that's about all. Those are those rules, and we finished that. Okay, ready for 8.6. All right, we're just about at the midpoint. Anyone need a break or would like to have a break? You know, Jake is so agreeable. He'll always say yes, won't he? Okay. All right, want to take one? We'll pick up from here when we come back. At least get up, move around, get some blood flowing. That's not the one. All right. We'll go from current slide. Still in Chapter 8, mostly integration techniques. And we may do a little bit of improper integrals, but they're not very proper. Well, never mind, we won't go there. But this section, we're not there yet. We're 8.6 is numerical integration. Now, in reality, I hate to break the news to you, but all this stuff we've been doing is great to know and good stuff, but in the real world, a lot of times your integration are things you're not going to be able to do analytically. Okay, all these techniques and stuff, it's just one little thing off, not going to happen. You know, so a lot of times you're going to wind up doing numerical integration. Now, some more. Hate to break the news to you. Most of the time, these are going to come in packages these days that you just buy the package and it does it for you, and you don't know and probably won't even care how it's doing them. But this is a calculus book, so it wants you to know what you're doing and how you're doing it. So we're going to show you a few techniques that are used by some of those packages in doing the numerical integration. So we're going to approximate a definite integral using the trapezoidal rule. We'll approximate a definite integral using Simpson's rule. And we'll analyze approximate errors in both the trapezoidal and Simpson's rule. Now, this book does things a little differently from most others I've taught from. Usually there's an intermediate in there called the midpoint rule. It's a little bit better than the trapezoid rule, and then when you combine it with the trapezoid rule, you get Simpson's rule. This book kind of leaves out the midpoint rule, but sort of brings it in a little bit later also. So let's start with the trapezoid rule. Some elementary functions simply do not have antiderivatives that are elementary functions. For example, there's no elementary function that has any one of the following as a derivative. The cube root of x times the square root of 1 minus x. Okay? And you can try to be your heart's content to try to wiggle, wangle, finagle around and get that to get in some form you can do it. You can't. Okay? Same thing here. The square root of x times cosine x. You would almost hope that maybe integration by parts might work with that one. It won't. Okay? Cosine x over x. Okay? No. Square root of 1 minus x cubed. Okay, that's not going to do it either. Sine of x squared. No. Okay? Not to do an antiderivative of any of those. If you needed to evaluate a definite integral that involved something like that, whose antiderivative cannot be found, not even hard to find, cannot be found, then the fundamental theorem of calculus is still true. It cannot be easily applied. Okay? In this case, it's easier to resort to an approximation technique. So that's what we do, numerical techniques. Okay? Now, and again, these are a couple. I think in reality, the packages you buy are probably going to do something they call finite differences. And there's another name, I can't remember what it is. They're very similar in titles. And basically, you just approximate that integral with a bunch of dx's and go from there. I know when I did my doctoral research, we were dealing with integrals that you can't take derivatives off, that had no antiderivative. So we had to do everything pretty much numerically. And had to be very careful doing it, that you kept within rules and stuff. And some of them took an awful long time to do the calculations. Of course, we were using little, y'all don't even know what I'm talking about, Apple II computers. You know what that is? That was before they had Macintoshes. Okay, long before they had Macintoshes. These were pretty simple little machines. But you can write the programs and have them do numerical integration for you. Okay? You just keep reducing your, it's almost like a Riemann sum. You just keep reducing the size of your interval, and then when your final answer gets within the tolerance of your previous answer was, you'd say you're not going to get much better, you stop. And I can remember, had probably the worst case of flu I ever remember having. I was doing my analysis of the data by that time, so I'd set up the problem, and it would go through the first iterations really quickly. Zip, zip, zip. I could just hear the printer printing them off, but after a while, a bit longer in between because it was doing more and more steps in there, and it was taking it longer and longer, and finally, it would be an awful long time. So I would set up the thing, get the problem running, make sure I had it right, I go to bed. And at first, zip, 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 and after a while, the zips got further and further apart. I'd go back to sleep, and then when I'd wake up, I wasn't hearing any zips as it printed the next line. I'd get up and look and see if it was through. If it was through, then I'd enter the next one and go back to bed. It was awful, but I was glad it took a while so I could sleep in between iterations. But anyway, there are times, in fact, it comes up really frequently, you have to use numerical techniques. We're going to do the trapezoid rule. Now, one of these is this, to approximate the definite integral using n trapezoids, okay? This is what it means by that. In the development of this method, assume that f is continuous. Okay, that's a very good assumption to make, because if it's not continuous, it's going to be awfully hard to do approximate integration. Okay, and we're going to assume it's positive. Okay, on this interval a to b. Okay, and we're trying to approximate this f of x dx. So what we do. Almost feels like we're going back to Riemann sums and stuff. But we break the range from A to B, x sub 0 is A, x sub n is B, into n equal, they don't really have to be, but usually they are, yeah, they almost always are equal divisions, okay? And you evaluate, because you know the function. The function's not the problem. It's just you can't integrate the function. So, break this. You know the first point, and you know the last point. So, b minus a is your interval. Divide that by 2, divide it by 4, divide it by however many ones you want to do. And this one is 4. So, you have 5 points here. X of 0, 1, 2, 3, and 4. It's 5 points there. You know the function, evaluate the function at each of those 5 points. Okay? Now, you approximate the area under the curve by the area under these trapezoids from these 5 values here. Okay? This one, obviously, the trapezoid overestimates the function by a little bit. Here, the trapezoid overestimates by a little bit more. And underestimates here, and is awfully close there. So you figure this is not going to be far off, okay? So that's basically what we do with the trapezoid rule, okay? Now let's sort of formalize that a little bit, okay? First, partition the interval A to B into n subintervals with the width of the delta x is that b minus a, that's the whole length, divided by n. That's what we did before. We showed b minus a divided by 4, so that was your delta x. Now, a will be the first one, and b will be the last one, and then all the rest of them, the x values will be a delta x more than the previous one. So x1 will be delta x plus x0, and then x2 will be delta x plus x1, which is 2 delta x plus x0, and on and on and on. Then form a trapezoid from each subinterval. The area of that ith trapezoid, okay, do you remember the area of a trapezoid, anybody? Oh, that was too long ago, wasn't it?
That's the base. Is that half of the base 1 plus base 2 times the base?
Yes, very good. Here's how I picture it. There's the trapezoid, right? Flip it over so that the long side is here and the short side is there. And you have exactly twice that, right? But then it squares off at the top and you have a rectangle. And the area of the rectangle is the width times the length, but the length is, like you said, base 1 plus base 2. Base 2 plus base 1. Doesn't matter. That's the length times the width. That happens to be our dx. Okay? And half of that would be the area of this. So 1/2. One base plus the other base times the width, height, whatever you want to call it, the other. Okay? Well, the delta x, remember, was b minus a over n. So this is 1/2 the f sub I minus 1 plus L sub I, okay? That's your 2 bases added together. Multiply that times the width. The delta x is b minus a over n, okay? So there's the area of that rectangle. We know this. We know what the function is. We can calculate its values. Add those two adjacent ones together, divide by 2, multiply it by the whole length divided by the number of intervals we have. Okay? So there's the area of any of the trapezoids. Well, this is the first one. This is any one, the ith one. This is x0 plus x1. After that, half that. All right. So that's your one section of one trapezoid. Well, you do a whole bunch of those, okay? And notice what you got. The b minus a over n, that's going to be constant, okay? That's the same. So just factor that out, okay? And then you have alpha of x0 plus alpha of x1 over 2, plus alpha of x1 plus alpha of x2 over 2, plus alpha of x2 plus, you know, you're repeating some of those. So except for the first one, that you only have alpha of x0 over 2, then you have alpha of x1 plus alpha of x2, but all I'm up to, and then half of that last one. So that's exactly what we do here, except pull the 2's out and put it 1 over 2n here, okay? And then you have once, these are once. The first one and the last one, one value, two values for all the rest of them, okay? That's the trapezoid. You know your b, you know your a, you know you chose what number of increments you're going to have, and then just do your calculations. Okay? Now, that's by formula, and it's fairly straightforward, and really not too hard to remember, perhaps. Okay? Now, this almost gets it to be a Riemann sum. Now you let n go to infinity, okay? Approach infinity. Your b minus a over 2n, that gets to be a bigger and bigger and bigger number, meaning a smaller and smaller and smaller delta x. And you do this, but you have a lot more of them. And this is what your numerical calculation will do. Basically, you take one division, and then basically divide it into each one into half. You've already done half the calculation, just do a few more. And all this is showing is that this comes out being your, if you take the limit of that and just rearrange, take the, yeah, there's the first and the last terms over 2, and then all the rest of them. See, I don't know why they do this. I would have left the over 2 in here, because that's what it's going to wind up here. But they took it out, then they put it back in as a delta x over 2, which is exactly what we had before. And then these 2's cancel out here, and it's just alpha of x delta x, and this comes out. Now, the thing is, as n goes to infinity, whatever this is, whatever it is, this is going to be greater, so that's going to 0, and that leaves you with the limit of alpha of x dx, which is what you're trying to calculate in the first place. So basically it's saying this is why the trapezoid rule works. If you just take the smaller and smaller increments, it'll do it. So here's the theorem. Did anyone need that a little longer? Oh, okay.
So is that last integral that's also equal to the area?
Yeah, and this is the area under the curve, yeah. This is the exact integral, which is what we started with a couple slides ago, went this way, and this shows you really did get this. Now, was that your question?
So I guess instead of having to add all of them up, you
Yeah.
can just do that.
Yeah, I know. But
Okay.
the trouble is, this is what you couldn't integrate in the first place.
Oh.
Yeah, it's like, don't get too fired up about it. But it's just showing that this does produce what you're looking for. It's just, you have a lot to do. But let this computer do the walking for you, okay? It can do that. That's what they're good at, you know, just taking smaller and smaller increments and keep going. And at some point, the difference between the previous one and the next one is going to be so small, you can't determine anyway, and let that be your answer. Okay, that's why it's an approximation. It's never exact, but it's a very good approximation. Okay, so here's the theorem. Let f be a continuous function. Remember, it had to be, but a to b. Sorry. The trapezoid rule for approximating this integral, which you can't integrate, that's the whole purpose of it, okay, would be approximately this. The b minus a over 2n, that's the 1/2 of your delta x, okay, and then get that in front, and then it's f of your first endpoint, and then twice the second, third, fourth, fifth, sixth, until you get to n, and just do one of those again. And as your ends get larger and larger and larger, the right-hand side of this gets closer and closer to real values. This you can't integrate. That's why you start. Now, what we're going to do is do something we can integrate, and we're going to compare and see how good we get with this. So here's example 1. And this is on page 560. Now, do y'all know what this is? The integral from 0 to pi of sine x dx? Any of you run into that? My younger brother used to work for an electric power company. He retired recently. Why am I still working? I'm not sure. But anyway, when they were calculating how much energy can be produced by the solar cells and things like this, it was approximately half a day, you know, and that was a sine curve. And so the radiation, so basically it came up with a sine curve, so they use this a lot to approximate. You know, they had to have the appropriate factors there. It's pretty easy to calculate. What's the antiderivative of sine x? This one we do know. It's negative cosine. Good. Thought that's what you said. Okay, so this will be minus the cosine x evaluated from 0 to pi. Okay, so what is cosine of pi? -1, and you got minus that, so that'd be a 1 minus, but then you got a minus, so it's plus the cosine at 0, and what's that? 1. And didn't know you'd be doing such high-level math today. 1 plus 1 is 2. Okay, so sure enough, the integral of sine x, the first lobe of that, from the first 0 to the second 0, that area under that is 2. Whatever your units are, it's 2. Okay, now, so what we're going to do, we know that one, but we're going to do the very thing for trapezoid rule when you have n equal 4 and n equal 8. Okay? And it's really a good idea. I know we know what the sine function looks like, but whatever function you have is to do this. Okay? When it's 4, then you have pi minus 0 divided by 4, so that would be pi fourths. So you have 0, pi fourths, pi halves, 3/4 pi, and pi. Okay? Now, what you want to do is calculate the value of the function at those 5 values. These two are easy. They're 0. Okay? So we only really have 3 to go. What's sine of pi fourths? 2 over 2. Sine of pi halves? 1. 3/4 pi? Square root of 2 over 2. Okay, and these are 0 and 0. Okay? Now, remember what your rule was. Do they call it T sub 4? In some books they do. Let's see. No, they didn't give it a name, did they? No. Sort of surprised at that. Okay. All right. But there's the rule anyway. And in some books, I'm going to do it this way just for, I'm used to doing it. T sub 4, that was n equal 4. It would be, how does it begin? B minus A over 2n. So what's your B? Pi minus 0 over, it's 2n, 8, right? See, over 2n. N was 4, this is 8, okay? Now, I rather use the 4, but, you know, this book uses the 8, okay? You just have to keep up with what you're doing from this point on. So it's f of 0, which is, of course, 0, plus twice this, twice pi halves over 2 would be twice pi halves over 2. Now, I'm sorry, where do I get pi halves? Root 2 over 2. Yeah. Twice root 2 over 2 is? Square root of 2. Plus twice 1. Plus twice root 2 over 2. Root 2 plus 0. Only do that one once. Okay. So what does this add up to? 2 plus 2 root 2 times pi divided by 8. So if someone wants to pull out a handy-dandy calculator and punch that in and see what you get. 2 plus 2 root 2 multiply that number by pi, divide by 8. You want to get anything yet?
1.896.
1.896. Not too awfully bad when you know the answer's 2. And you'll notice there, every one of these underestimates a little bit, so it's not surprising that's a little bit short of what we're looking for. Okay? Now, what we're going to do is do the same thing for these values, but I know this one's 0, and I know that one's 0. I know this one is root 2 over 2, and this one's 1, and this one's root 2 over 2. We got to calculate the others, and you got to use a calculator for that too, because I don't know those. Okay, so do sine of pi eighths. Somebody?
0.0068.
0.00. Are you in radian mode? Yeah, good. Okay. That was way too small a number. Whoops, my eraser's not working. Wait. Okay. Second, 0.38. You going to leave it there? Let's take it at least one more. Second? 382. Is that what you said? Okay. And the next one, sine of 3/8 pi. 924. I bet you this one will be 0.924, right? And this one I bet you is going to be 0.382. Okay. All right. So T8 will be still 0 to pi, but this time we're divided by 2 times 8 is 16. And then we're going to add these up. 0 plus twice that would be 0.764 plus, I really should do 4 times because you got one on each side. But I'll worry about that later. I'm going to put my root 2 because I know that's going to be that, plus 2. Oops, I left off that one. Plus 2 times that is 1.848. Yeah, plus another 1.848 plus another root 2 plus another 0.764 plus, that's it. Okay. Now, if we had been smart about it, we'd have left that total we had in here before and just added these. 4 times this, 4 times plus 4 times that, plus 4 times that, plus 4 times that. But we weren't smart enough to do that, so we didn't. And actually, more precisely, if you went on and put in your sine of pi eighths, sine of 3/8 pi, it's more typing, but I thought if we just typed it once, then we just put numbers in. But someone do that if you can and will. And I sure hope we'll get something in between 1.9 and 2. I know it's a pain in the neck, but someone's got to do it. Anyone got an answer yet?
I got 2.4.
2.4.
I got 1.97.
That sounds a lot better. Okay. 1.97 what? 1.974. That's getting awful close to 2, isn't it? Okay. And that with some round off in there as well. So not going to take me long till I'm going to say that's close enough. You know, I'm happy with that answer. Okay. So that's because we knew what the answer was. All right. And they got, for the first one, 1.896, and the second one, 1.974. So we did pretty well there. They say that most graphing utilities, I don't know this for a fact because when I back had a graphing calculator, it died years ago, so I haven't bothered to get another one, have a numerical integration feature, and it talks about a few things. And they do point something out to you. What if your graphing calculator, you had tried to do this, the integral from -1 to 2 times 1 over x dx, and you tried to get a graph of that, and it gave you an error? Is there any reason why it should have given you an error? Say again?
Goes to -1.
Okay, and the reason you say that, this actually is a log, right? We know that. And you can't take the log of -1. Okay? Another fundamental reason, you're graphing from -1 to 2, which includes the number 0, and 1 over 0 is undefined. So they're both really the same reasons. You can't do it. Okay? So you can't just feed anything into those things and expect to get decent answers, because you have to put something that's reasonable in the first place. So just because you have the utility doesn't mean it can do miracles that can't be done anywhere else. Now, this is something, I couldn't remember how they did it, but here's what they do. They say, it is interesting to compare the trapezoid rule with the midpoint rule given in section 4.2. That's it. Back in 4.2, they gave you a midpoint rule. I thought I had seen this somewhere before. Okay. So the book has gone over the midpoint rule. The trapezoid rule actually works a midpoint rule is more precise, but the trapezoid rule is a little bit easier to operate. Okay? So let's see what they say about it. Oh, we did all this work. Let's see how they did it. When n is equal to 4, delta x is equal to pi fourths. We got that. And we obtained this integral to be 1/8, pi eighths, which is b minus a, pi, over 2n. 2 times 4 is 8. And then you do sine of 0 plus 2 times sine of pi fourths, blah, blah, blah. Okay? We know sine of 0 is 0, and sine of pi fourths is root 2 over 2. So this would be root 2 over 2 plus 2 plus root 2 over 2. So that means plus root 2. And that's going to be pretty easy to evaluate. And there they did it. I've got such glare I can't read it. And we did that. So it would be pi times, okay, I didn't do that, but you could have. They divided numerator and the denominator by 2. So pi times 1 plus root 2 over 4, and came out 1.896. Okay. Then when you jumped up to 8 intervals, and you use delta x equal 8, then that would be pi over 16. Delta x is pi eighths. Then you do the sine of 0 for twice sine of pi eighths. And if you had just left the other thing in there, the sum that you did, which had this one, that one, this one, and that one in it, then all you had to do was plus 2 sine of pi eighths plus 2 sine. And actually, because this is the same as that, 4 times the sine of pi eighths plus 4 times the sine of 3/8 pi, and then hit equals, then you would have then multiplied it by pi 16ths. Yeah, and that's exactly what they did here. What we did before, 2 plus 2 root 2 plus 4 times sine of pi eighths plus 4 times sine of 3/8 pi. That's all you had to do. And then that came out 1.974, approximately. There's round off, definitely. Okay? For this particular integral, you could have found the antiderivative and determined the exact area to be 2, which we had done to begin with. Now, what we didn't do was midpoint rule, and I really won't want to go to it in great detail, but I want to go back and just at least show it to you to tell you what we mean by midpoint rule. So let's take this one. Let's take the midpoint between pi fourths and pi 0 and pi fourths, and that would be pi eighths. And at that point, we're going to evaluate the function right there. I can't get that to disappear. There it goes. Okay. And then draw the best curve that goes through the tangent at the midpoint. Okay. And then we'll do this midpoint and do the tangent at the midpoint there. Okay. I can't get it to draw. Okay, something like that. And what you do is you wind up getting an overestimate of it. Okay. And it's actually a little bit better overestimate than this was an underestimate. Well, if you combine those two together and do the point, and you do the same thing here, and you get better. Combine them together and take the average of them. Just put them together, basically. That gives you what they call Simpson's rule. And another way you can approach Simpson's rule, I'll get to this in a second. One way to view the trapezoidal approximation of a definite integral is to say that on each subinterval you approximate F by a first-degree polynomial, a linear polynomial. That's the line between the 2 points. In Simpson's rule, you take the procedure one step further, approximate F by the second-degree polynomial. The best parabola you can make between this point and that point, and I think the midpoint. I think that's what you do. The best parabola there. And before presenting Simpson's rule, consider the following theorem for evaluating Simpson's integrals of polynomials of degree 2. Okay? So here's your polynomial, degree 2, ax squared plus bx plus c. Most of the time I'm used to those being lowercase, but it's okay for uppercase. If that's your polynomial, then the integral from a to b of this is just a theorem they came up with somewhere, and it doesn't quite seem fair, but it is, okay? It's p of the first endpoint, p of the last endpoint, and then we're going to do p of the average between these two, b plus a over 2. So that's the midpoint between a and b, okay? All right. So that p is evaluated at that one, and you do 4 times that middle. And they don't tell you where they get the 4, okay? It is right. I wish they had done it a little bit more rigorously here. They just sort of throw this at you. Now, here's another thing bizarre here. Your preceding factor is b minus a, which it always was, but not divided by, this would have, if you just had the 2 points, 1 point in between, that would be a 2. This is a 6, okay? And they haven't told you why that's the case either. But we'll sort of let that go right now. This is just a theorem. You're supposed to accept it. That this is your approximation of the integral of a second degree polynomial. That this is a good approximation of it. Okay. I don't like this approach to this at all. Okay. To develop Simpson's rule for approximating a definite integral, you again partition the interval a to b into n subintervals, and we'll do the same as before. The delta x is going to be b minus a divided by n. This time, however, it's required that n be even. Before it could be anything. Okay? This one requires that n is even. And the subintervals are grouped into pairs, okay? So that you go from x0 to x2, so this one's in the middle, x2 to x4 with x3 in the middle, x4 to x6 with x5 in the middle, and on like this, x of, now remember, you had to have an even number, so that's an even number, so n minus 2, you will have an n minus 1, and they all work out. That last one is your b, the first one's your a. On each double subinterval, okay, you can approximate f by a polynomial p degree less than or equal to 2, okay? We're going to use degree 2, using that formula from the last theorem. Again, this is really, the way they present it almost seems like hocus pocus, but it works. It does work. This is indeed what you come up with. So, here's a pretty good representation of it, okay? On the subinterval of 0 to 2, right here, 0 to 2, x of 0 to x of 2, choose a polynomial of least degree passing through the points x0, y0, x1, y1, and x2, y2. Now, it's not going to be a straight line. It's the polynomial that does that. And that would be degree 2. The lowest degree you can have that will fit those 3 points is the parabola. Now, this is the curve you're talking about. And you're talking about the area under this curve, the blue area right here, okay? Now, the polynomial that fits that would be go through here, here, and there. Goes to the midpoint and both of the endpoints. Now, the trapezoid would have gone through like this. Not a good approximation. This parabola makes a much better approximation. Yeah, you're missing some here. It's overestimating here, but underestimating here. And those two areas are closer than it would have been if you just on a straight line between this point and that point, which is what the trapezoid rule. That would have overestimated big time with no underestimation. Okay. Now, we then claim the area under the curve, the polynomial curve between x of 0 and x of 2 is approximately what it is under the function alpha factor x of 0 to x of 2. All right. I really don't care for this approach at all. All right. Now, using p as the approximation of f on this interval, we have this. Now, if you remember what that approximation was from that previous theorem, it's b minus a over 6, not over 2. No, that was in the thing. You count the first value once, the midpoint value 4 times, and the last value once. Okay? Now, what we're going to do now is multiply just in here this by 2 over 2 and this by 2 over 2, so you have the same denominator here. And then they're going to take that 2 and factor it here, so it moves it up here, and you, well, this term right here is your x1. That's halfway between x0 and x2. That's your x1, okay? Which is what I was saying earlier. So that then yields this. The x2 minus x0 is b minus a over n, which is 2, and this 2 is going to wipe out that one, so you get back to exactly what you had before. Now, then the 2 and the 6 divide out, and you have over 3n. So b minus a over 3n, which is where that 6 was anyway. 2 times 3 is 6. Okay? And then you have this polynomial approximation. Now, if you do that over a bigger interval and you break them down, every one of them, you're going to count this one again. You're going to do from x2 to x4. So you have 2 of your x2s. You have 4 of your x3s. You have an x4 here, but if you do it again, then you'll have 2 x4s. So for every one you do, you're going to increase this one by 1 and make it 2. So you have 1, 4, 2, 4, 2, 4, 2, 4. That last one's just going to be a 1. Okay? Repeating that procedure will produce this theorem. Okay? F be a continuous function on a to b, n be an even integer. Okay? Have just any integer, even integer. Simpson's rule for approximating this integral for f, then, continuous function f, will be approximately b minus a over 3n. Before it was b minus a over 2n, remember? Now it's 3n. Bigger denominator, meaning it's going to be a smaller thing you multiply. Okay? Now, you've got n of these divisions, that's an even number. So the first one's counted once, then 4, 2, 4, 2, 4, 2, 4, 2, 4, and then 1 again. The first one, last one are once each, and every other one, the evens are twice and the odds are once. Okay, 4 times. And then, of course, as n is going to infinity, this is going to get closer and closer to that. Okay. How are we doing on time? Oh, we got time. Let's do this one. These can be tedious, folks, okay? But we already know the answer to this one, don't we? And we're going to compare results for n equal 4 and n equal 8. We did this with trapezoid rule. We know what those answers are, so let's do it here. All right? So what I'm going to call this is S sub 4, Simpson's rule for 4. All right? Reminding yourselves, b minus a over 3n. So again, that's pi minus 0 is pi divided by 3 times 4 is 12. Okay? That's the b minus a over 3n, where n is 4. Okay? Now, times. Sine of 0 plus 4 times the sine of pi fourths, right? Plus 2 times the sine of pi halves, plus 4 times the sine of pi, 3 pi over 4, plus sine of pi. Okay, these two we know to be 0. All right. So this is pi 12ths times. Okay. Well, 4 times root 2 over 2 is 2 root 2 plus 2 plus 2 root 2. So this is pi over 12 times 4 root 2 plus 2, and you can divide out a 2, and that would be pi 6 times 2 root 2 plus 1. I hope I did that right. I was going faster than I intended to go. And by the way, this larsoncalculus.com, you can see an interactive version of this. And what do we get? Anything yet?
I got like 2.004.
With what follows the 4? 5. Okay, so round that up. Approximately 2.005. Now think about the trapezoid rule at 4, same number of subdivisions, 1.8 something another. Whoa! I mean, that was not good to 1 decimal place. This is good to almost 3. You know, it's definitely good to 2, and getting pretty close to 3. Okay? Now, if we can, on the same page, I don't know if you lost your stuff or not, S sub 8 would be, remember it's pi, that stays the same, over 3 times n, that would be 24. And remember that first one's going to be 0, so let's not write that one down. It just takes up room. That would be 4 times the sine of pi 8ths, only we're going to double that and make it 8 times the sine of pi 8ths, plus 4 times the sine of pi fourths, plus 8 times the sine of 3/8 pi, plus 4 times the sine of pi halves. Nope, that's just 2 times the sine of pi halves, because you only got one of those. That's going to be it, because that took care of both sides. okay? This is sine of pi and sine of 7/8 pi. This is sine of pi fourths and 3/4 pi. This is sine of, same thing we did before, only with our new coefficients in there. See what that gives you. Anybody got it yet? Pretty exciting stuff, though, isn't it? .000243. Let's just round to one day. Oh my goodness! Now we're good to almost 4 decimal points. Okay. Whoa! And that's the same division we had before. And last time with trapezoid rule, it was 1.9 something. We thought that was really good. You know, we're sort of good to 1 decimal point. Now we're good to almost 4. Okay. So yeah, this gets there a lot sooner, a lot faster, a lot more accurately than trapezoid rule. Okay. Now, yes.
Can we get back to the slide real quick with
The one before this? That? Oh, okay, sorry. Okay, that all you need? Okay. Now, I think I need to erase my mess so you can see how the book did it. I think it comes out pretty close to what we did. So let's see. When n equal 4, you have that approximately being pi over 12. 3 times 4 is 12. Times sine 0, which is 0. 4 times sine pi fourths, 2 times sine pi halves, 4 times sine pi 3/4 pi, and then 1 times sine of pi, which is 0. And that comes up about 2.005, okay? Which is really, really accurate just at 4 intervals, okay? When you do 8, you come up, they don't show you any of the intermediate things. They just say 2.0003. You're getting really, really good accuracy from very few subdivisions, okay? All right. Now a little bit of error analysis. When you use an approximation technique, it is important to know how accurate you can expect the approximation to be. Now, this following theorem gives formulas for estimating the errors involved in the use of Simpson's rule and the trapezoid rule, and I think I can easily say the proof of this is beyond the scope of this course, okay? Don't know if they're going to say that, but I believe it probably will be. If f has a continuous second derivative, okay, that's a requirement for the error analysis to work. Continuous second derivative on the interval a to b, then the error in approximating this by the trapezoid rule, I don't know why yeah, okay. Up here that says Simpsons and trapezoid, here they say trapezoid and Simpsons, it makes more sense. The error, absolute error, is going to be less than this interval b minus a cubed. Okay, now first what's that telling you? The bigger your interval you're trying to estimate this, your error is going to go up really by the cube of that. So that could be pretty hazardous. Divided by 12n squared, well, now we got that n, number of intervals squared. It's in the denominator. That's a pretty decent coefficient, coefficient down there. So that's not. Now the next part is the maximum of the absolute value of your second derivative, which means when you evaluate that second derivative of that function f, you have to basically kind of either mentally or actually draw a graph, get the maximum value positive or negative, take the absolute value of that, that's going to be your next factor. And that's any time x is between a and b. Now, sometimes that maximum value will be at the endpoint, either a or b. Sometimes it'll be in the middle, so you have to evaluate all those. Okay. Now, moreover, if f has a continuous fourth derivative on a to b, then the error approximated by the Simpson's rule is, okay, b minus a to the fifth, so that's actually gotten worse, especially if the error, if the interval has gotten bigger, okay? But look at the denominator. 180 as opposed to 12, that's a significant increase, and into the fourth. And these are in your denominator, so the more terms you have, wow, your precision gets much better. Times the max of that fourth derivative. And again, you have to basically, sorry, I'm having trouble breathing. Maximize, well, you have to take that fourth derivative and then figure out on that interval where that's about its maximum. Positive or negative, absolute value of that is what you put in there. But this is pretty insignificant compared to what's going on here, especially in those denominators. Okay. In general, when using an approximation, you think of the error E as the difference between the integral and the approximation. Now, theorem H6 states that the errors generated by trapezoid and Simpson's rule have upper bounds dependent on the extreme values of that second derivative and fourth derivative. Second derivative from trapezoid, fourth derivative for Simpson's rule. Simpson's method. Okay. Furthermore, those errors can be made arbitrarily small by increasing the n, providing that the f double prime f second derivative and fourth derivative are continuous, and therefore bounded on the a to b. Sort of a lot of blah, blah, blah. So let's do example 3. And we'll determine the value of n such that the trapezoid rule will approximate the value of this integral here, which guess what? Would a tangent substitution work on that? And I think it would, but let's not, okay? I don't want to get into that. With an error that is less than or equal to 0.01. You need to come up with an n. How many spaces do you need? Now, if you think this is just sort of a wasted academic exercise, well, you're probably a little bit right there, but this isn't talking about statistics here, but you do this kind of stuff in statistics all the time. If you're trying to model a population, data set, whatever you're trying to model, and you're trying to get find out how many subjects you need to try to get the power of your situation, you're doing almost this kind of thing. This is almost like that type of a calculation. You're finding how big an n you need in order to get this within an error that you find acceptable. Okay? Not quite the same thing, but close. So if we go to our error, and this is for the trapezoid rule, so we want the error to be less than or equal to 0.01. So that's the 0.01 less than or equal to I was looking for b minus a. I see it now. That would be 1 raised to the third power, which is still 1, okay, divided by 12n squared times the maximum of the second derivative of this. So the first thing we've got to do here is take f of x equal 1 plus x squared to the 1/2 power. Okay? Take a derivative of it. F prime of x is equal to? Anybody? Not that hard. Anyone? Earth students, come in, please.
2/3.
Okay. Did I hear a 2/3?
Yeah, 2/3 times.
First derivative? This is a 1/2 here.
You're gonna add. Sorry.
Okay. It's 1/2 1 plus x squared to the minus 1/2 power times 2x, right? Chain rule, power rule. Got it? Okay. Now, let's rewrite that. These 2's will disappear, and that gives you basically x over 1 plus x squared, square root of 1 plus x squared. Well, no, let's not do that. Sorry. We need to take second derivative first before we do anything silly like that. So let's leave this as sort of simplified version, x times 1 plus x squared to the minus 1/2. But that's your first derivative. We need to go, remember, second derivative. Okay? So f double prime of x is equal to what? Now it's a product rule. How does that go? Okay, a little louder.
Derivative of the first term times the term plus derivative of the second term.
Oh, okay. Okay, you're telling me what the rule is. The first times derivative of the second plus the second times derivative of the first. Is that what you're saying? Yeah, okay. So first would be x, and what's the derivative of the second one? Negative 1/2. 1 plus x squared to the minus 3/2. 3/2. Ooh, that's ugly. Let's try that again. Okay. Times another 2x, right? That's just the first term, okay? Those 2's will go out. We'll worry about the rest of it later. That's the first times derivative of the second, plus the second, which is 1 plus x squared to the mega 1/2, times derivative of the first, which is what? All right. So that's what we've got. So there's your second derivative. Okay. Now we'll write that in a little more reasonable form. That's going to be an x squared, because you got an x here and an x there. It's going to be a minus in front over 1 plus x squared to the 3/2 power, plus 1 plus, now is that really a, yeah, I guess it is. Trying to make sure I haven't lost any terms. 1 plus x squared, well, 1 over that to the 1/2 power. Okay. Now, we want to get the maximum value of that. Now I'm going to shoot for an endpoint. When you plug a 0 in for x, the first term goes to 0, the second term goes to 1. right? Okay. Plug a 1 in there. The first term is a minus 1 over say again?
I think it's like the cube root of 4.
Okay, wait. I can't hear it. A little loud.
The cube root of 4.
Yeah. Did you say cube root? Where did the cube root? Oh, okay. Yeah, okay. Got what you're saying. Yeah, the cube root. No, it's the square root of. We put a 1 in there. Yeah, it'd be 2. 2 cubed is 8. It's the square root of 8. Okay. That's in the denominator. Okay. So 1 over the square root of 8 plus, and what's the next one? 1 over the square root of 2. So the first one's a minus 1 over the square root of 8 plus 1 over root 2, I think. Okay. Now, that's an ugly 8, isn't it? There could be somewhere in the middle there that it's different, but just come up with approximately what that answer is. Minus 1 over root 8 plus 1 over root 2. Anyone got anything yet? Let's just see what the book's getting. They say the maximum value of that is when at 0. I forgot to add the second part, which is 1. When x is 0, it's 1. This is going to be something less than 1. So we're going to go with 1. And that's going to be pretty easy to go with, okay? All right. So what we have now is 12 n, or 0.12 n squared is less than or equal to 1. So divide that, n squared is less than or equal to 1 divided by 0.12. So n is less than or equal to 1 over the square root of 0.12. So someone figure out what that is. That shouldn't be too hard to do. It's going to be about between 0.3 and 4 in the denominator, so 1 divided by that. Anybody get something? This thing right here shouldn't be that bad. What's that? Yeah, 3. N is about 3. 2.8, but you can't have 2.8 division, so let's make it 3. Okay. Now, and they proceed to, they didn't ask you to do this, but they proceed to do the trapezoid rule and come up with 1.154, and then if you're within 0.01, so that's within 1.14 and 1.16. If your precision is 0.01, I don't see why they carry the extra digit, but I guess they can because they want to. So you're somewhere in that range. Just seems like a lot of busy work. Okay. Well, let's see. They're going to do it, so let's watch them do it. You erase all the ink, and we're almost out of time, so let's get it done. By letting f of x be that, which of course it is, first derivative is that which we got, second derivative, boy, we didn't get something that simple, did we? Did it come out that way? I thought we had another term on it. And then the maximum value of that on the interval 0 to 1 would be at 0, which is 1. So then we had the error is less than or equal to that, which is 1 over 12 squared. So you want that to be less than, I don't know why they did it this way, but it is okay. You want that to be 0.01. So if you put 0.01 here, and they wrote it as 1 over 100, and then they just flipped the inequality. But yeah, and they switch sides too. You have to do that. This to me is so many ways to make errors between these two, but that's exactly what they got. And they got 1.28. We got the same thing without doing those magical things. Now, it said choose the n equal 3 has to be greater than or equal to the 2.89, so do 3, and this is what the trapezoid rule gives you, and that's going to be a pretty good approximation. Where's the answer? There it is, 1.154. So you know you're within 1.14 and 1.16. All right. Whew. Homework exercises here. Any of the odds 3 through 13. They're all at Calc Chat. 3's at Calc View. 15 through 23, they're all at Calc Chat. 17's at Calc View. 25 or 27, both at Calc Chat. 25's at Calc View. 29 or 31, they're both at Calc Chat. 29's at Calc View. 33's at Calc Chat. And then you can do any of the, either 35 or 37, they're both should be at Calc Chat. 39, you can explore doing that if you'd like. That's it, should be at Calc Chat. And then any of the odds 41 through 45, they should all be at Calc Chat. There's a proof at 47 if you want to do that. All right. Where we'll start next time is integration by tables, which we've already done a little bit of. We're going to do a bit more and practice doing those. And then we're not going to do much on improper integrals. If they're not proper, you shouldn't be doing. No, we just don't have time. So we'll after we finish 8-7, I'll knock on wood, try to have your test ready for you. So that'll probably be Monday. Okay? So try to get your second test in by Monday so you can get your third test. I mean, I'll give it to you anyway, but don't get too far behind, folks. Okay?
Or the first test in by Monday so we can get the second test.
Oh yeah, first test. I'm sorry. my Cal 1 class just had their third, so yeah, first class in by Monday.
Second test.
So yeah, so you can have that. Sorry, I thought you needed a little adrenaline at the end of the class. Okay, panic. Okay, good deal.